So now I'll talk about some extensions of the chain rule for functions of several variables. So suppose f of x is a differentiable function. And so here I'm starting out again just as functions of one variable, and then we'll try and generalize from there. And x is equal to g of t, where g of t is also a differentiable function. Then I can think of f as a function of t just by, first I'll calculate x by evaluating g at t, and then I'll evaluate f at that number. And so then this is the single variable chain rule. I have derivative of f with respect to t is equal to derivative of f with respect to x times the derivative of x with respect to t. And so if I want to evaluate the log of cosine of t with respect to t, so here log is playing the role of f and cosine is playing the role of g. So f is equal to log of x and x is equal to cosine of t. So x is equal to g of t is equal to cosine of t. So to take the derivative of this, it's going to be a straightforward application of the chain rule. So the derivative of f with respect to x, so that's the logarithm. The derivative of the logarithm is just 1 over x. Oh, and I guess this reminds me of something. So somebody asked me after class last time, what's the difference between log and natural log? And so for this class, I actually mean the same thing. So when I write log just like this, I mean log with the base e. If I want it to be a log with a different base, I'll write log sub base. So, it'll be log and then subscript 10 would be what your log button on, old calculators used to do. I'm doing it this way just because later in the course we'll be using a program called R. And when you use the log function in R, it calculates a natural logarithm, even though it's spelled log. And generally, in mathematics, when you get sort of further along, log means natural log, and in engineering, you have ln for natural logarithm. Okay, so 1 over x is the derivative of log x when the log function is using e as its base. So here, when I take the derivative of f, I get 1 over x, and then I have to multiply that times dx dt. And so here, g of t, or dx dt, is just going to be the derivative of cosine of t with respect to t, so that's minus sine of t. So then I end up with minus 1 over cosine of t, so x, remember, is cosine of t, times the sine of t, and that's equal to, so sine of t divided by cosine of t, that's the tangent of t, and so then it's negative. So I get minus tangent of t. So now let's see what happens when we have a function of two variables. So f of xy, it's differentiable again. This time, I'm going to define x to be a function g of t and y to be a function h of t, where g and h are also both differentiable functions. But in this specific case now, f is a function of two variables, but g and h are both functions of t. So f of xy is actually only a function of one variable. It's sort of like in the pricing formula I had in the first set of slides. I had this d1 and d2. They are both functions of the same variables. I guess that'll be a better example when I let g and h be functions of more than one variable. But essentially what you're sort of doing is you're getting to a function of t by way of a function of x and y. And so I can think of f of xy if I if I replace the x just by g of t, which gives me my x coordinate, and by h of t, y by h of t, which gives me my y coordinate, then this function here is really just a function of t, and its derivative, so here I'm getting kind of clever with the d's and the partial symbols. So because f is only a function of one variable t, I can actually write a complete derivative for f. But the way I'm going to get that is I'm going to take the partial derivative of f with respect to x. So that's going to be a function of x and y. But then by the chain rule, I have to multiply this by, so this is going to be du dt. So g prime of t. So whatever gave me this. So here it's going to be advantageous to use the other notation, which will be in the next line. And then I'm also going to take the partial derivative with respect of f with respect to y. That's going to be a function of x and y again, but then I have to evaluate that, multiply that by h prime of t. So this is the chain rule popping out again. But what I'm trying to do is capture how f is going to react to a change in x and how f is going to react to a change in y, and then multiply that by how fast those are changing with respect to t. When I add those together, that's going to be giving me my full derivative of f with respect to t. And this is not something you're supposed to just look at and understand. This is sort of the definition of the chain rule when I define a function this way. And so it's a little bit more clear when I write out the chain rule using this notation. So I have df dt, so the full derivative of f with respect to t. So I just take the partial of f with respect to x and multiply that times the derivative of x with respect to t. And then I do the same thing with the partial derivative of f with respect to y times the derivative of y with respect to t. And so here f is a function of two variables, so I have to think of doing partial derivatives. But here x and y, these are just functions of a single variable t, so I get full derivatives there. So we can do a quick example of this. So suppose I let f of xy equal x squared plus y plus xy cubed. Then x is equal to e to the 2t, and y is equal to t squared. So first, just to make sure that I'm not selling snake oil, I suppose, I'm going to do this by a direct computation. So one way to make this into a function of t alone is just to, in the function itself, replace x by e to the 2t and replace all the y's by t squareds. So if I do that, I get f of t is e to the 4t, so that's just e to the 2t squared. T squared, that came from my y. And then y cubed is going to give me t to the 6th, and the x is going to give me e to the 2t. And then I'll take the derivative of this with respect to t. So it's pretty easy. I can do the first two just term by term. So here I've cheated a little bit with the chain rule. I skipped doing the substitution, but that's 4e to the 4t. T squared by the power rule is just going to be 2t. And then here I have a function of t times another function of t, so I have to use the product rule. So that says derivative of the first function, so derivative of t to the 6th is 6t to the 5th, times the second function, plus the first function times the derivative of the second function. And so that tells me that the derivative of f with respect to t is this expression here. And let's see. Yeah, so that's as simple as it's going to get, so it's not particularly pretty. But it's also ugly enough that if we get exactly the same thing, I'm not going to think that it just happened by chance. So we'll try this again, this time using the chain rule. So first I'm going to calculate all the pieces I need. So I'll need the derivative of f with respect to x, the partial derivative of f with respect to x. So that's pretty easy to see just by using linearity and the power rule. And the partial derivative of f with respect to y. And then I need the derivative of x with respect to t. So that's 2e to the 2t. And the derivative of y with respect to t. So that's just 2t. So remember, x was equal to e to the 2t, and y was equal to t squared. And so now my expression for the derivative with respect to t of f of xy was the partial of f with respect to x times the derivative of x with respect to t plus the derivative of partial of f with respect to y times the derivative of y with respect to t. So I'll just go ahead and from the things I've already calculated, plug those in. So hopefully it's clear where all of that came from. Just each one of these shows up here. And now I need to get the answer in terms of t, so I'll just substitute in the expressions for t for x and y. Okay. And then I just do a little bit of simplification. And I think, so let's see, I put it in the terms with the polynomial bit descending. So I have a t to the 6th term, a t to the 5th term, a t term, and a t to the 0 term. Just, that's how I'm going to put these in order. And so was that, go back to the last thing. So here I had t to the 6th term, 2e to the 2t, t to the 5th term, t term, and t to the 0 term. So using the chain rule, we got the same result that we did using the direct calculation. Okay, and so now we'll let, again, f of xy be a differentiable function. But now we're going to allow x to be a function of two other variables and y to be a function of the same two other variables. So we can write x as a function of s and t and y as a function of s and t. And here g and h, so these functions that give me x and t, x and y also need to be differentiable functions. So then if I rewrite the function like this, I can think of my function f as a function of s and t. And I can write the derivatives. So now, because f of x is again, or f is again a function of two variables, I've just changed variables from x and y to s and t. I'm going to end up with two partials for f. So I'll have partial f, partial s. And there I'm just going to get that by, both of these are equivalent, just depending on whether you want to think of the name of the function that gives you x as x, or if you want to consider it g. But essentially, I just have to add up the partials that give me my partial with respect to s. So I take the partial of f with respect to s times the partial of f with respect to x times the partial of x with respect to s. And I'm going to add that to partial of f with respect to y times the partial of y with respect to s. And that sort of captures all of the dependence of my function f on the variable s. And then I can do exactly the same thing for the variable t. And so in general, if f is a function of n variables, and for each I in 1 to n, xi, so all I'm saying here is each one of those variables is in turn a function of m other variables, then the partial derivative of f with respect to tj, so t is one of my sort of second level variables, is given by this formula. So it just says the partial of f with respect to tj is equal to the sum of the partial of f with respect to each argument of f times the partial of that argument with respect to tj. So really what I'm trying to do is just capture all of the dependence of f on this tj and add those together. And that's going to give me the partial of f with respect to t sub j. And I worked through a very complicated example of this as well. So I'll just let you look at how I'm setting it up. So I have f is now a function of 3 variables, given by this, again, not very pretty expression. And then each one of the arguments of f, so x1, x2, x3, is in turn a function of 2 variables. So that means that even though when I want to look at f, or when I write down f, I see 3 things here. There's really only kind of 2 degrees of freedom. There's t1 and t2 that are affecting how f changes. And to calculate the partial, I'm just going to take the partial of f with respect to the first argument times the partial of that with respect to t1, add that to the same thing for the second argument, and add that to the same thing for the third argument. I think I actually did all of this, but it's just algebra, so you have it on the slide if you would like to go through it. It comes from the textbook too, so I think the reason I chose to do this was just I was reading the book and thought that's way too complicated to go sort of directly from here to here. So now you have an explanation if you need it.